Okay, this device is an oscilloscope. It's used to measure voltages and frequencies of DC and AC circuits, mostly AC. And I just want to show you that these two inputs here are voltage inputs, and what happens to this line when I apply the batteries to it, you can see the voltage, the line jumps, which shows it's measuring a voltage. So the inputs to the oscilloscope are voltage inputs. And actually all this is a dot. It's a dot moving across the screen. I'll decrease the intensity a little bit here, and I can make it go faster and faster and faster. What controls the speed of this is this time per division switch here, and it tells the time it takes to cross one division. You see all those little squares on the screen here? Those are the divisions. So the time it takes to pass one division is the time noted here. For example, right now we're set at 0.1 seconds, which means it takes a tenth of a second for it to cross a square. So it should take 1 second to cross all 10 squares. We can make it go faster and faster and faster. That's the time per division switch. The voltage switch is the sensitivity of the voltage coming in, the measurement of the voltage. So for example, if I connect the battery again, you can see I can increase the sensitivity of that. It jumps more if I set it to a more sensitive setting on the volts per division. So what the volts per division switch shows us is how many volts are measured by each division on the screen. Okay, so the first thing we're going to do is the first procedure in your handout. We're looking at the oscilloscope handout in your lab manual. This is on page 51. And we're just going to jump over here to page 55 and take a look at what's called the sweep velocity, which is what's written on which is what indicated on the time per division switch. So it tells us to set the time per division switch to 0.5 seconds per centimeter. So if I turn this to, that's the first setting, 0.5. It says 0.5 here, and this is seconds. And we're going to check to see if this is really true. What we're going to do is actually time how long it takes to cross 10 divisions. We're going to write that down on your data page, 10 divisions and the time. Then we're going to calculate the time per division by dividing the time by the number of divisions. So let's actually do that. What I'm going to do is time how long it takes for the little bright dot to go 10 divisions. I'm going to catch it just as it starts. Drop. If you touch the wrong thing. Okay, here we go. As soon as it appears on the left-hand side of the screen, I'm going to start the timer. Boom. Now you can see I'm timing it, going across the screen, 10 divisions. Boom. 4.9 seconds. So you should write that number, 4.9 as 10 divisions. It took 4.9 seconds. When you divide those two, you should get 0.5 seconds per centimeter. I can obviously, if you divide this by 10, it's going to be 4.9. So that's our percent error. If we increase the time per division to the 0.2 setting, notice it's going a little faster now. So now we can write 0.2 divisions traveled, no, 10 divisions traveled, and at the 0.2 seconds per centimeter, let's take how long it takes to go across those 10 divisions. Okay, here we go. Boom. Little response time there. Okay, so I got hey, that's not too bad. So 1.97 seconds is what you would write in your data page. Divide this by the 10 and you'll get 0.19 seconds per centimeter, which is very close to what's indicated on the oscilloscope. 0.1 second per division. Let's try it. I'm going to try to measure. It's going fast now, so my human response time is going to be probably a bigger error. But I'm going to try to start the stopwatch just as it appears on the left-hand side and stop it over here. Here we go. Boom. Oops. Oh, that's not too good. Okay, so that's not too bad, actually. 1.06 divided by 10 is 0.106 seconds per centimeter per division, and that's what we indicate here. So, okay, so the whole point of this was to confirm that these numbers are true. This is how many seconds it takes to cross one division of the screen. Now notice that if we increase the speed, it goes faster and faster. Here we have 20 milliseconds, 10 milliseconds, 5 thousandths of a second to cross one square. And if we go fast enough, we get what looks like a straight line, but you know it's really just a dot moving really, really fast across the screen. Okay, we can also use this device to measure voltages. So this is our voltage input, and this is the sensitivity of the voltage. As we turn this knob, it becomes more and more sensitive to the voltage input. The instructions are to start with a 2 volt per division setting. So here we have 2 volts per division. Now I'm going to use this position knob, you see the up and down arrows here, to set this right on the 0 mark, the 0 line. Now this says 2, so that means 2 volts for each division. So let me connect this to the voltmeter, and we'll see how far it actually goes. And just clip this to our, I've got 2 D cells here. Theoretically it should be around 3 volts, but they're kind of old batteries, so it'll probably be a little bit less. So here I go. I'm going to connect this, the voltage input from the 2 batteries, and I like it to go up so we could be a little bit more intuitive. Okay, it jumped up. It jumped up to 1 division, and if you read the little ticks in between, it looks like 1.2, 1.4. So it's 1.4 divisions, and the calculated voltage of the battery is 1.4 times 2, that's 2.8 volts. But we didn't measure the voltage of the battery yet, so let's do that and see what the battery really is putting out. So I'm going to grab the voltmeter, DC volts, and put it at the 20 volt scale. And we're going to measure the voltage of the battery directly. Just connecting the leads. And we're getting 2.97. So that's the number you want to write on your data page, where it says voltage of the battery is measured by the voltmeter is 2.97 volts. And we just saw that it jumped 1.4 times 2, that's 2.8, not too bad. And then you will calculate the percent difference between those 2 values. Now let's make it more sensitive and go to the 1 volt per division setting. What do you expect is going to happen? Of course, it's going to jump even more than before because it's more sensitive. Wow, look at that. It jumped from the 0 line, 1, 2, looks like about 2.9, a little more than 2.9 volts, 2.9 divisions. So the number of divisions is 2.9, and so times 1 volt per division, so that's 2.9 volts. 2.9 volts, and then you take the percent difference between that and the voltage that you wrote up here. Okay, so there's one more. We want to set it to the even more sensitive setting, 0.5 volts per division. Right there, volts per division. And connect okay, it's off the scale, so it's jumping off the scale, so we can't really do that. So just scratch that measurement. You don't need to do that. Okay, so that's DC. DC is what we're using the oscilloscope for is a very expensive and glorified voltmeter. That's basically all it was doing there. So now, instead of DC, we're going to take a look at a much more interesting situation of AC current. AC voltage actually. Okay, now that we've used this as a voltmeter to measure DC voltage, we want to measure some AC voltage. I've got a signal generator here that's putting out a sine wave, and you can see it's set to about 100 times 0.7. It's about 70 hertz this is set at. So I'm going to plug this into our input, and now with the switch up to AC, you can see the waveform. You can see that we can increase the wavelength and decrease it, decrease the frequency, increase the frequency. And so this gives us a good idea of what the waveform looks like. That's one of the things oscilloscopes are used for, is to check the shape of a waveform coming out of some electronic component. So what controls this, as the faster the little dot sweeps, now it's sweeping faster, and so it spreads the waveform out. Now slower, and it's all scrunched up. So what we want to do is, first of all, we're going to use this to measure the voltage of the AC waveform. And in order to compare it with the real voltage, I'm just going to take our voltmeter, which is set at AC voltage, 20 volts, and I'm going to measure the voltage of this, of the frequency generator just coming right out of it. Now this is RMS. This is the RMS voltage reading. The root mean squared, in other words, it's a sine wave, but this is measuring the sort of the average of the voltage coming out, and we're getting 3.51 volts RMS coming out of the frequency generator, and that's the number that you should write on your data page, AC measurements, page 56. You should write 3.51 volts right up here where it says VRMS. RMS voltage signal coming from the signal generator, 3.51. So now we know what that voltage is. Let's see if we can measure it on our oscilloscope. All right, so we've got a frequency generator here that generates an AC signal. So now we're going to use the oscilloscope to show the AC waveform. That's one of the things oscilloscopes are used for, is to check out the waveform of an electronic component. And so we remember, vertically we're measuring voltage, and on the horizontal axis we're measuring time, basically, how fast it's going across the screen. So let's check the voltage output of this AC generator, frequency generator. I'm going to measure the AC voltage by just plugging the voltmeter right in here. It looks like we're getting, that's DC, sorry about that. Looks like we're getting about 3.56 volts AC, and that's the number that you should write up here where it says RMS voltage of the signal generator right here. So this is measuring RMS voltage. Remember, the sine wave has a peak-to-peak voltage and a root mean squared, or sort of an average voltage. That's what the voltmeter is measuring. So we've got that RMS voltage measured. I'm going to plug this back into the oscilloscope and see if the oscilloscope agrees with that measurement. All right, so now we have the waveform shown on the oscilloscope, and we can measure the peak-to-peak voltage. As you can see on your data page, it says number of divisions peak-to-peak vertically. First, we need to note the volts per division setting. So the volts per division setting is where the black line is pointing to 2 volts per division, which means each division is 2 volts, and it's asking us to measure the number of divisions peak to peak vertically. That means from this peak vertically down to that peak. So I'm going to adjust this so the top peak is right on a line, and I'm going to count the divisions. 1, 2, 3, 4, almost exactly 5 divisions. So we'd write 5.0 divisions, and the peak-to-peak voltage would be 5.0 times our 2 volts per division setting. Now remember, that's peak-to-peak voltage. What we want to do is find the RMS voltage so we can compare with the voltmeter reading. So to get from the peak-to-peak to the RMS, first we divide by 2, because the amplitude is defined as from 0 to the peak, not from peak to peak, so we divide by 2. And we take that and divide by 1.41, which is 1 over the square root of 2, to get the RMS voltage. Then you compare that RMS voltage with the one from the meter and get the percent difference between the two. Okay, so that shows how we can use the oscilloscope to measure the voltage of an AC signal. An interesting thing that happens, we can demonstrate with this, is a device called a diode. A diode is like a little valve. It only lets current flow one way. It cuts off the direction the other way. So what I'm going to do is take this little diode, and I'm going to place it right across the contacts, the connectors here. Just place it right across there. So what this is going to do, when the current flows one way, it's going to show on the oscilloscope. When it flows the other way, it's going to get shorted out by this diode and won't reach the oscilloscope. So what we do is touch it there, and you can see the top form of this wave has been shorted out or cut out by the diode, because the diode only lets the current flow one way, not the other way. If I turn the diode around the other direction, you can see now the bottom of the wave has been cut off. Current can only flow positive, it can't flow negative. The diode is a really useful device for converting AC current to DC current. You can put it together with other diodes to make it more efficient. So on your data page, you should actually sketch this waveform in the space where it says sketch the sine wave with a diode in the circuit, and then sketch it with a diode the other way in the circuit in the other space. Okay, so another thing that the oscilloscope is useful for is measuring the frequency ratios between two devices. If we have two frequency generators, normally the time controls the horizontal with your time per division switch, and the voltage controls the vertical. But what we're going to do now is reconfigure the oscilloscope so that one sine wave is controlling the vertical and another sine wave is controlling the horizontal. In order to do that, I'm going to set these two to about the same setting, 90 Hertz. So we've got one frequency generator connected to the vertical, and the other one is going to be connected to the horizontal, like this. So what's happening here is the lower frequency generator is making a little bright dot go up and down. The other frequency generator is making it go left and right. So the little dot is going left and right and up and down at the same time. When the two are in phase, it's a straight line, lower left to upper right. But if they're 90 degrees out of phase, we get the dot going left and right. At a different time, it's going up and down, and so we get this circle. If I could exactly match the frequencies, it stops. So they're 90 degrees out of phase. Now, what if we made it go up and down twice every time it goes left and right once? That would be a 2 to 4 ratio. This, by the way, is called a Lissajous pattern, and you can see the spelling of that in your lab handout booklet. So now I'm going to double the frequency. Actually, that's controlling the horizontal. So let me go back and do it with this one. There it is right there. So the vertical is now twice the horizontal. You can see the two peaks here. It's just going up and down twice every time it goes back and forth, left and right, once. Your instructions in the lab manual are to try to sketch this, but it's really hard to hold it steady. I don't know if you can pause this while you're watching it. Will they be able to pause this?
Yeah.
And then you can get a nice sketch of it. That's a 2 to 1 vertical to horizontal ratio. And I'm going to take it up to 3 to 1. There it is. Now you see, no, that's actually 3 to 2. This is even more interesting. Notice there's 3 peaks. It's really hard to get this to stop. 3 vertical peaks and 2 horizontal peaks, which means there's a 3 to 2 vertical to horizontal pattern. Let's see if I can get the 3 to 1. Okay, so we've got, okay, 1, 3. There's 3 to 1. Notice there's 3 peaks vertically and 1 horizontally. So you can see what the ratio is between the 2 frequencies of these frequency generators just by watching the Lisa-Zhu pattern. And you can get more complex patterns as well. Okay, that concludes our oscilloscope